We're going to start our final segment of the course now on the Earth's climate, which will constitute chapters 12, 13, and 14. Here in chapter 12, we're going to talk about what climate is and the different types of climate. Chapter 13, we'll talk about climate change, and chapter 14 will end with air pollution. So we have lots of different climates. It is impossible to even finish numbering the different types of climates that our Earth has. Everywhere you go has a different climate. Even going from one house to a different house has a different climate. But we can make general categorizations, general ways to identify one climate from another. The main variables that help us to do that are latitude, land versus water, ocean currents, prevailing winds, pressure cells, mountain barriers, altitude, and there are a whole lot of other variables that help distinguish one climate from another. So for example, let's take a look here at global temperatures. Look in the southern hemisphere first of all. These temperature isotherms are relatively straight. So basically this is just a function of latitude. As you go further and further south, the temperature gets colder and colder. Makes sense, pretty straightforward. But notice in the northern hemisphere, it doesn't do that. Basically, what we see in the southern hemisphere is simply a function of latitude. But in the northern hemisphere, we have to also take into account land versus water. Land will cool faster than water, so where at one latitude you're at about 50 degrees Celsius in the ocean, the land will cool off faster and you're down to about 35 or maybe even down to 20 like we are here in North America. So land versus water makes a huge difference as well. We also have ocean currents. Here, let's take a look at the Atlantic. Remember that we have an ocean current that's pushing to the north. Well, what's that going to do as it comes up? It's going to keep the northern water in the Atlantic warmer a little bit longer. And the cold starts pushing down, and notice you have kinks in these isotherms because of that cold water going down, going southward. So you see lots of kinks and bends in these isotherms due to ocean currents and also the differences between land and water. Precipitation. Where can we usually find precipitation? Well, we usually find those in the global circulation models where you have rising motion. In other words, the low pressure of the ITCZ and the subpolar lows at 60 degrees north. That's where you're usually going to see your precipitation. So you get your rainforests, and then you get your lush green farmland and other green areas in the northern latitudes. Really nice areas up there. Whereas, what do you see at 30 degrees latitude and at the poles? Well, there you have the sinking motion from the circulation cells, and so you end up with a high pressure system. High pressure, sinking air, not much precipitation. This is where you usually have your deserts. And believe it or not, the North Pole and the South Pole are both deserts. They are both classified as a type of desert. Not the same kind of desert as what you would see here at 30 degrees latitude, but it's still a desert nonetheless. Why? Because there's a huge lack of precipitation, and despite all the snow and the ice up there, if you were to melt that down, it wouldn't constitute much water at all. So it is technically a desert. So here is a generalized idea of what things would look like. At the ITCZ, you have rising motion. Here you have your Hadley cells causing rising motion at the ITCZ, but at 30 degrees latitude, it's sinking motion as it merges with the Ferrel cells. And then you end up with your polar cells between 60 degrees and 90 degrees latitude. So you can see where it goes. How can we expect our climates to look like? Well, we would expect very wet weather at the poles, dry weather at 30 degrees latitude, wet weather around 60 degrees latitude, and dry again at the poles. And then you end up having transition zones here in between 0, 30, and 60 degrees latitudes. Okay, so this is great. We have a good basic understanding of how to distinguish one climate from another, except for one problem. This is a very generalized model. For example, we live here in Daytona Beach, Florida. Anyone know the latitude of Daytona Beach? It's somewhere around 30 degrees latitude, 30 degrees north. So according to this, we should be in a desert. That's where we should be. Why isn't Florida a desert? Well, because you have other variables. We have the Gulf of Mexico. Really, if it weren't for the Gulf of Mexico, Florida would be a desert. But since we have the Gulf of Mexico, that adding that extra variable, it isn't. And so we have to look at more than one variable to be able to distinguish one climate from another. So here is another example. You have San Francisco, Kansas City, and Baltimore, which are all pretty much on the same latitude. San Francisco's at 37 degrees north. Kansas City and Baltimore are both at 39 degrees. Baltimore, yeah, it's wet all year round. And that has a lot to do with the, Atlantic Ocean currents. Kansas City is quite humid in the summer, but dry in the winter. Why? Well, in the summer, you get a lot of weather coming in from the Gulf of Mexico. Yet San Francisco is extremely dry in the summer. Why? Because their primary weather is coming from the west, and their ocean currents are coming from the north. So they get cold, dry air. And sometimes it does get a little bit humid since it's from the ocean, but really, since the North Pacific up here is colder, you don't get a lot of water vapor in the air. So there's another good example of how we can't generalize climates. Now, how can things change from one? Here's another way that things can change from one place to another, even if it's the same latitude. Here we're looking at the West Coast, looking at Santa Cruz and San Jose, California. You have water coming in from the ocean. It goes over the Coast Range Mountains. You get some condensation, produce clouds, produce precipitation over each of these small ranges. And then the air continues and then hits the Sierra Nevadas and really starts to produce a lot of precipitation. And then on the backside, you end up in a rain shadow. Remember when we talked about rain shadows a few chapters back? We've talked about that a few times. Chapter 8 when we talked about air masses. We talked about it, I believe it was chapter 5 where we talked about it as well. A couple times we've talked about this. So you end up with a modified air mass that has lost all its water due to rain and precipitation over the 3 mountain ranges. And because it's lost water, it's descending. Every time it rises, it cools at 6 degrees, so it cools a little bit, but then descends on the other side at 10 degrees Celsius per kilometer. So it heats up at a very much faster rate. So already your air is hotter when you reach San Jose. Even hotter when you reach Los Baños and Merced. Then once you reach the other side, Death Valley, it is insanely dry and hot. You can see that effect in a smaller range, even in places where you would least expect it. Here we're looking at Washington State with the Olympic Mountains here. On the windward side, in other words, on the east side of the Olympic Mountains, you have what's called the Hoh rainforest. Is it really a rainforest? Not a tropical rainforest, but it does get quite a bit of precipitation because of these mountains here. And so you can see they get 134 inches of rain a year. That's even rivaling, probably even surpassing what we get here in Florida. So they get a lot of precipitation there. Just go a few miles away to Port Townsend on the other side of the mountains. Barely a little more than a tenth of what they get in the Hoh rainforest. Quite dry, quite dry, because they live in a rain shadow.